Today we're going to talk about our new model, and someone gently hinted me that this title might be a bit too wordy. So just talk about a new model, never mind what it's called. Adversarial example is going to be something that I will define and will overtalk during the next 10 minutes. And machine learning can be also said AI, people like it better. And it's also not my own work, it's a joint work with my old lab, which is my advisor, Professor Adversarial. So what are we going to talk about today? So everyone knows AI, everyone knows how magnificent it is. It's going to take all our jobs and control the world and everything. For example, if your job is drawing an armchair of the shape of avocado, you are no longer needed in this world. Because this model of OpenAI can easily do it instead of you in a really inspiring way. So there is also ChatGPT, if you want to chat about an imaginary Christopher Columbus maybe on your after time. And there is a Whisper that Tirza was mentioned before me that can transcript an audio file into the text if you are in a boring meter that you don't want to hear, but maybe you do want to read. So you can do that. So everyone knows the application in the medical world, which is going to change the world. For example, this model can help radiologists to know which area in the images you need to look more carefully about, where there's hemorrhages or maybe tumors and all kinds of things like that will support the radiology work. But wait, why is it working? So the theory is so far behind that currently is considered as miracles. And we don't know almost anything about how it's working. But today we're going to talk about much simpler task than curing cancer. Just going to talk about image classification. So what is image classification? If I have this image of a pig, all I want in this world is just to know, well, this is a pig. Why is image classification is even important to us? Sooner or later we're going to have autonomous cars. Your car will going to take pictures of the world and try to understand how to drive by itself. For example, she's going to see signs. I need to see the sign and then say, well, this is a stop sign, and eventually stop. But what happens if someone will just mislead this network? So what are adversarial example? We're talking about classification. So some evil guy, of course, girl, the one to just see some car accident can take a regular stop sign and add these tiny rectangles that it does not interrupt you to see, oh, well, this is a stop sign. But when your car is going to see this stop sign, it will say, oh, this is a speed limit sign, and particularly won't stop. So what an adversarial example is a bit more formal definition. I'm going to say every input image, every stop sign, for example, have a nearby adversarial example, meaning an image that looks almost the same to you, but will be classified differently. So I can take any stop sign and just add this specially crafted noise that for human, we're totally robust to it, but the car will get confused and will not stop. Great. So let's start from the beginning, how we classify signs. So if I give you these stop signs and these speed limit signs, how would you classify one over the other? So you can say, well, this is red. It's written stop. This one's rectangular. It's written speed limit. There is the number 45. You have all these kind of criteria that you can differentiate those two groups. And if I give you this stop sign, you say, well, this is red. This is also an hexagon. This is it's clearly written stop. So it's going to be here. But for some reason, the AI classification is taking it to the other group. Although for us, it seems nothing like a speed limit sign. Okay? So what are we doing in our research? We need to understand this phenomena. Why can anyone take a stop sign and just make it a speed limit sign without changing the image? And if we know how it works, we're going to try to fight it. Great. So we said that the AI classified this thing wrong. But why does it do it? So let's see how AI is looking at those images. So first, you just throw everything on this grid. Okay? Because it's a computer, you know math. Okay. So these images are not really images for him. It's just these points in the space. Now, what the classifier needs to do is to distinguish one class from another. In other words, just draw some function that if you're falling this side of the function, you're going to be a stop sign. And if the dot is from the other side of the function, it's going to be a speed limit sign. But what our adversarial phenomena says, it says next to some point of stop sign, there is the adversarial example, a bit noisy stop sign. It's really, really close to it, but it's still going to be classified differently. So this classification function is no longer valid for us. But it's not only next to this stop sign, it's next to any stop sign. I can add this particular noise to any stop sign and make it a speed limit sign. And not only that, I can do it for all speed limit signs. Just add a small perturbation and make it classified as a stop sign. So which function will we draw that encapsulate this reality? So what we are saying in our lab is stop looking at it in this 2D image, look at it in 3D. And if you're already 3D, flip this image on its back. And if this image is flipped on its back, I can draw a function that will separate these two clusters. So I have this blue function f, and everything below the function is going to be classified as a stop sign, all the red dots, and all the green dots will classify it as speed limit signs because it's above f. Great. So in these settings, where are the adversarial examples? Right above or right below. So I have really close to any stop sign, I have here something that look like a stop sign, but it's still classified as a speed limit sign because it's above f. Great. So our stop sign will be just above. And now you can ask me, well, Odelia, in real-life data, there is no beautiful cluster that you just need to cut in the middle. Real-life data are everywhere. So I say, no problem, because I have my Dimpled manifold. Don't tell Eli I said Dimpled manifold. I can just go slightly beneath and slightly above every data sample just to classify it correctly. And still here, every red dot have a nearby adversarial example. I have a blue one underneath. And every blue dot have a red one in the other side of this boundary, of this function. Great. So let's talk an adversarial example that is even more scary than our stop sign. So the real-world adversarial example, you can take an image of a pig and add a really small noise and get another image of a pig that will be classified as an airliner. So these two pigs looks completely the same. Unlike the stop sign that as humans we can say is, okay, something weird is going with this bad stop sign. Here, you can look at this pig all day long and you will never find the difference between this image and that image. And there are like real-life examples. This is really classified as an airliner. I'm not cheating. So you say, well, Odelia, now I'm worried what I'm going to do with the Tesla I just bought. So maybe let's talk a tiny silver lining in the end. What is robustness? If we want to be robust to this phenomena, what are we going to do? So if according to our model, the boundary is just a dimple above and beneath all the data points, all we need to do is just make those dimples a bit deeper, right? If we're going to cross a little higher and a little lower underneath and above the point, the adversarial example will be further away. It will be more easily distinguished from the original image. For example, if in these settings you take the stop sign, so you can see in here, it's going in the left one, it's going to be above the function, but in the right one, it's going to be beneath. So it's be also classified as a stop sign. Great. So what are we talking? I need you to take one message with you home. I'll say, play with the ChatGPT and try to troll it, and even harass it, it's okay. And you're going to get a really funny result, and you can send to all your friends on Twitter. Twitter is loaded for that. But please, just stay awake while you're driving your Tesla.